Okay, so today we are going to be talking about Newton's second law. So this is the big equation that you probably already know, but we are going to be learning how to use it, how to find the net force, how to find the acceleration, and things like that. So the big equation, Newton's second law, is force is equal to mass times acceleration. Again, you've probably already seen this equation before. So F is the net force on the object, and I will talk about what net force means in a bit. That is in newtons. M is the mass of the object, and that's measured in kilograms, which you guys already know. And then A is the acceleration of the object, and that is measured in meters per second squared. So that's our big equation. Now, another way to examine this equation is solving the equation for acceleration. So the reason we do this is we can kind of see how the object accelerates when different forces are acting on the object, or the object is a bigger or a smaller mass. Now, before we talked about Newton's first law, which was an object at rest stays at rest, an object in motion stays in motion unless acted upon by an unbalanced force. So with Newton's first law, that was kind of when we had balanced forces on the object. Either the object stayed in motion or it stayed at rest. Now here we have unbalanced forces. So when the forces are unbalanced, we have an acceleration. Okay, so this is where this equation here comes in. So that equation, or the acceleration, I mean, depends directly upon the net force, meaning when force is bigger or net force is bigger, acceleration is bigger. When force is smaller, acceleration is smaller. They're directly proportional. And also, it depends inversely upon the object's mass, meaning when the mass is huge, the acceleration is small. When the mass is small, acceleration is big. And this makes sense, right? We talked about inertia last week. We talked about how when you have a big, huge boulder, it's going to be really, really hard to move because the mass is so big, the inertia is so big, and therefore, because it's hard to move, the acceleration will be very, very small. If you have a little tiny stone, then that mass is small, the acceleration can be bigger. All right, so that's how this relationship is with this equation here. So let's do an example right away. We have a 3,000 kilogram plane has to accelerate at 12 meters per second in order to take off. What force do the engines have to give to the plane in order to accomplish this? So I know that I have my equation, force is equal to mass times acceleration. Now, the givens that I have here is that the mass of the plane is 3,000 kilograms. I also know that it has to accelerate at 12 meters per second squared. So now that I know these variables, I can plug them into my equation. So I get force is equal to mass, which is 3,000 kilograms, times acceleration, which is 12 meters per second squared. And then I can plug this into my calculator. So I get 3,000 times 12, and I end up getting 36,000. So 36,000, and the unit for force is newtons. So there is my answer. Okay, so of course, here we're not taking into account frictional forces or anything like that, or air resistance. This is just a very simple Newton's laws problem. All right, so that's how you're going to use that equation. Okay, so let's talk about this whole thing, net force, what that means. Now, net force is the sum of all forces on the object. So you'll see the symbol either F sub net, meaning net force, or you'll also see the sigma. This is what it's like a sideways M or a sideways W kind of. You might have seen it before in your math class. It means sum. All right, so what does sum mean? What does net mean? Basically, it's like the total force on the object, or the overall force on the object. So it seems kind of scary at first when you see these symbols, but if I show you these pictures, so if I asked you what the net force on the object below was, what would you say? So here I have two 5 Newton forces, and those are both to the right. So what would you say that the net force is in that case? If you said 10 newtons, to the right, then you're correct, right? So all we do is add those two things together. I have 5 newtons plus 5 newtons, we get 10 newtons, and it is directed toward the right. Now, force is a vector, which means that we have to give the direction of that force. So that's why I have to the right there as well. Now, another example, we have 5 newtons to the right, and we have 3 newtons to the left. So what would you say the net force on that object is? If you said 2 newtons to the right, you are correct. All right, so this one's a little bit more tricky because we have 1 force to the right and 1 force to the left. Now, in your brain, if you said 2 newtons, you already did this in your brain. You assigned one direction a positive direction and one direction a negative direction because that 3 newtons is kind of taking away from the 5 newtons, right? So that's kind of like a negative force. It's holding that 5 newtons back. So really what we're doing here is we are subtracting 3 from 5. Now, when we do this net force, really what we're doing is we are adding these forces together, but we're adding a negative, meaning when I say net force is equal to mass times acceleration, this is what we're examining right here. In this example with the 5 newtons and the 3 newtons, what you did in your brain is 5 newtons minus 3 newtons equals 2 newtons. But really what we're doing here is we are saying that that 5 Newton force is in the positive direction and that 3 Newton force is in the negative direction. So we're just adding these two things together. I have 5 newtons plus a negative 3 newtons, and that equals 2 newtons. So that's what a net force means when we're adding those two things together, okay? And then last but not least, if I have 5 newtons to the right and 5 newtons to the left, what's my net force? If you said 0, you're correct, right? There's no net force here. Some people say these forces cancel out, which is a correct term to use as well. Here we have balanced forces. So since the forces are balanced, the force is canceled out. We have no net force, therefore we have no acceleration because we know for Newton's second law, it's net force equals mass times acceleration, or in force net. This is both the same thing. Both of those equations mean the same thing because that sigma F and F sub net, those both mean the same thing. Now, if we have no net force, that means we have no acceleration, 0 acceleration, okay? So when forces are balanced, like they are here, we have no acceleration. All right, so let's do another example. If you push a 2-kilogram chair across a frictionless floor with a force of 5 newtons, what is the acceleration? So here, we learned how to draw free body diagrams last week. So with all these problems, you should be drawing a free body diagram, okay? Always, always, always. So we have our box, our free body diagram box. I am pushing a 2-kilogram chair across a frictionless floor. So that means my applied force is to the right, and it says it's the force of 5 newtons. So I'm actually just going to write that in there. And then also I know that I'm on the earth, so I have the force of gravity down, and that chair is sitting on the floor. So I have a force of the floor holding that chair up, and that we call the normal force. All right, so there's my normal force. Now I also want to write down my givens. I know that the mass of the chair is 2 kilograms. I know that force applied is 5 newtons, and then I know I want to find the acceleration. So in order to do that, all I have to do is apply Newton's second law. So I know that the net force is equal to mass times acceleration. In this case, my applied force is the only force that's acting on this object. All right, so that is my net force, 5 newtons to the right. So that makes my math easy, okay? So I end up getting 5 newtons equals the mass of the chair, which is 2 kilograms, times acceleration. And then all I have to do is I'm going to divide both sides by 2 kilograms to get that acceleration by itself. So 2 kilograms cancels out with 2 kilograms. And I end up getting an acceleration of 2.5 meters per second squared. All right, and that's my answer. All right, let's see example number 3. All right, so now it says, if you now push the same 2-kilogram chair across the floor with a force of 5 newtons, but there is a friction force of 3 newtons present, what is the acceleration? So now I need a new free body diagram. All right, I need a new free body diagram. So here is my chair. It's a beautiful chair, I know. I have, again, my applied force to the right. I'm going to call that the 5 Newton applied force. And then I know that I have now a friction force in the opposite direction. Remember, friction opposes the motion of the object. So that's going to be 3 newtons to the left. And then again, I have force of gravity down and normal force upwards. So now I again have a mass of the chair of 2 kilograms still, and then I have both my forces written on my free body diagram, and I want to know the new acceleration. So just like before, I'm going to write down my Newton's second law equation. So we get net force equals mass times acceleration. Now, net force in this case is made up of both the applied force and the friction force. So really, I have to add these things together. But remember, I say that one direction is positive and one direction is negative. So I'm going to say, okay, force applied is the positive force, and then my force of friction is my negative direction. So force applied minus force of friction equals mass times acceleration. Okay, and now all I'm going to do is I'm going to plug in my numbers here. So I get applied force, 5 newtons. That was a weird 5. Let me erase that and redo it. 5 newtons minus friction force, 3 newtons, equals the mass of the object, 2 kilograms, times acceleration. Okay, so 5 minus 3, that's easy. It's just 2 newtons, equals 2 kilograms times acceleration. I divide both sides by 2, which you probably already did in your head, but we'll just do it. 2 cancels out here, and we end up getting an acceleration of 1 meter per second squared. All right, and that's my answer. So in your head, you probably did, okay, 5 minus 3, that's 2. That's easy peasy. But I do want you guys to kind of get in the habit of writing this equation down right here and actually writing in your variables before you plug in your numbers, because it will help you practice and it will help you understand a little bit better as well. Okay, so let's talk about the force of gravity. So force of gravity is how we stay on the earth, right? How do our feet stay planted on the earth? Why do things fall towards the earth? It's because of the force of gravity. It's keeping us on the earth. It's pulling things down toward the center of the earth. Now we know that the force of gravity attracts objects toward the earth's center at an acceleration of 9.8 meters per second squared. Right? That's the acceleration of gravity. Now, force of gravity is different from the acceleration of gravity. Now, we already know that the force from Newton's second law equals mass times acceleration. So when we're talking about the force of gravity, we're talking about the acceleration of gravity for the acceleration in this equation here. So everything has the same acceleration of gravity on the Earth, which is at 9.8 meters per second squared. So they all fall toward the Earth at the same rate. However, the force of gravity is going to pull things down differently, meaning if something has a bigger mass, they're going to have a bigger force of gravity, because we can see mass, say I have a 10 kilogram object or a 2 kilogram object. The 10 kilogram object will have a bigger force of gravity because it has a bigger mass. All right. So that's what force of gravity is. So let's do an example, another example. If I have a cat right here and it has a mass of 5 kilograms, I want to know what is the acceleration of the cat as it's in free fall. Well, the cat is falling down towards Earth, towards the center of the Earth or the surface of the Earth. So what's the acceleration? Well, if you said 9.8 meters per second squared, you're correct, right? As something falls, the acceleration is always going to be 9.8 meters per second squared when that thing is on the earth. Now, of course, when we have something like air resistance, it is going to slow it down a little bit. So the acceleration is going to be a little bit lower, but we'll do an example of that in a second. But when something is falling towards the earth, the acceleration is going to be 9.8 meters per second squared. Now, what is the force pulling that cat down towards the earth? Now, if I drew a free body diagram of that cat and say there's no air resistance, it would just look like this, right? The force of gravity is what's pulling that cat down towards the earth. So remember, force of gravity is just going to be mass times acceleration of gravity. So if I want to know the force of gravity, all I have to do is plug in the mass of the cat, which is 5 kilograms, times the acceleration of gravity, 9.8 meters per second squared. And then I get 5 times 9.8, 49 newtons. All right, so that is the force of gravity acting on that cat, pulling it down towards the earth. Now, there is an application of this thing called the force of gravity, okay? And we're going to talk about that in a second. Now, if we look at this astronaut in this GIF at the side of the PowerPoint right here, we can see that he kind of floats in the air, right? Or kind of bounces. And you've probably seen videos of astronauts on the moon before when they're kind of bouncing and they look lighter, right? So why do astronauts bounce when they're on the moon? Why are they lighter? What is different about it? Okay. Now, what's happening here is their weight is less. But what is this thing called weight? Now, there's two different things, and you can see the title of the slide here, weight versus mass. They sound very similar, and in common English, we do say our weight. But these words are actually not interchangeable. They're actually different. They're related, but they're different. Okay, so mass is the amount of matter an object has. So meaning the amount of stuff like my body is made up of. If I have, say, my mass is about 65 kilograms, that mass, even if I go to the moon, my stuff of my body is not going to change, right? That's not going to change unless you're growing very, very fast. So like if you're a kid and you're growing up and your mass is changing, or say if I eat a bunch of hamburgers and I gain, so in English speak, we say gain weight, but really if you're eating hamburgers, you're going to gain mass. Or if I exercise a lot, and I'm losing, quote, weight, really I'm losing mass there, okay? So that mass is not going to change if you just go to the moon. You're still going to have the same amount of stuff your body is made up of, okay? And here's my corny joke. I know that I've said this before, but remember, you have mass, so you matter. The amount of matter. Get it? Get it? Oh, so funny. I know it's terrible. I'm sorry. Science jokes. Now, on the other hand, weight is the force of gravity acting on the object. So just like we were doing with that cat and we found the force of gravity acting on the cat, really what we just did is we found the weight of the cat. Okay, and so you can see that this is actually going to depend on the acceleration of gravity of the planet that that object is on. So the weight is the force of gravity, which is equal to mass times acceleration of gravity. So my weight would be my mass, 65 kilograms, times the acceleration of gravity on Earth, which is 9.8 meters per second squared, which is about 637 newtons. Now, of course, this weight is in newtons. We weigh things in pounds in the United States, and weight, or pounds really, is also a unit of weight. So it also has to do with the acceleration of gravity. So this is why astronauts look like they weigh less on the moon, is because they do weigh less. The reason for that is because the acceleration of gravity on the moon is much, much less than this 9.8 meters per second squared. All right, so that's why they look lighter, is because they do weigh less. Their mass is not less, their weight is less. All right, so mass doesn't change unless you gain a bunch of mass by eating a bunch of hamburgers, or you lose a bunch of mass by working out a ton. And weight can change depending on what planet you're on. So our weight is not going to change on Earth if we're staying on Earth, but if you go to the moon, your weight will change. So if the acceleration of gravity on the moon is 1.62 meters per second squared, what would be my weight there? So remember, force of gravity is weight, which is mass times acceleration of gravity. So if I want to know what my weight will be on the moon, I take my mass, which is about 65 kilograms, and I am going to multiply that by the acceleration of gravity on the moon, which is about 1.62 meters per second squared. So if I plug this into my calculator, I get 65 times 1.62, and we get 105.3 newtons. So I see that I weigh much, much less on the moon, 105.3 newtons, than I do on the Earth, 637 newtons. So this is why astronauts look lighter on the moon, is because they weigh less. All right, one last example. Example number 5, we have this cat has a mass of 5 kilograms. What is the cat's weight? Now remember, again, weight is the force of gravity, which is mass times acceleration of gravity. So the weight of the cat is going to be the mass, 5 kilograms, times the acceleration of gravity on the Earth, 9.8 meters per second squared. So 5 times 9.8, we already found that, if you remember, and that was 49 newtons. Okay, so that's the weight of the cat. And then we have, if there was an air resistance force, as this cat is falling, of 10 newtons opposing the cat's fall, what would be the new acceleration? So this is kind of bringing everything together, right? So we end up, well, first and foremost, we want to draw a free body diagram. So I have my cat. I know it's a beautiful, beautiful cat. Wait a second, let's make this a little bit better, okay? So I have my box. I'm going to draw some cat ears and then maybe some whiskers too. Yeah, that's better. Now remember, this cat is falling towards the Earth, but cats always land on their feet, right? So they're going to be totally fine. So we have the force of gravity acting downwards on that cat, pulling it down towards the Earth. And then we have the air resistance. Remember, air resistance is kind of like friction. It acts in the opposite direction of the motion. So here I'm just going to put force air up like that. So I want to know what the acceleration is. Now, this air resistance force is 10 newtons. Now, we know that this cat still has a mass of 5 kilograms, and we just found the cat's weight, or in other words, the force of gravity. So we know that the force of gravity is 49 newtons. So now what we want to do is we want to find what the acceleration of that cat is going to be. So I'm going to use Newton's second law. We know that the net force is equal to mass times acceleration. So net force in this case, I'm going to say down is positive, meaning this force of gravity is going to be the positive force, and then the air resistance is going to be the negative force. You can make any direction positive in these problems. It really doesn't matter as long as you keep your signs consistent, okay? So net force is going to be made up of a positive force of gravity minus the force of air resistance, because that is the negative force, okay? So we get force of gravity minus the force of air resistance equals mass of the cat times acceleration of the cat. And now we're going to plug in our numbers here. So we get force of gravity, which was 49 newtons, minus the force of air resistance, which was 10 newtons, equals the mass of the cat, which was 5 kilograms. So remember, mass and weight are different. We want mass in kilograms for that M there, and then times acceleration, which we're trying to find. So we get 49 minus 10, that ends up being 39 newtons, equals 5 kilograms. That's a weird 5. I'm sorry, my 5s are so weird. 5 kilograms times acceleration. I'm now going to divide both sides by 5 to get rid of that 5 on that side and get the acceleration by itself. And so here I end up getting, let's plug it into our calculator, 39 divided by 5. And I get that the acceleration is 7.8 meters per second squared. And that makes sense because the air resistance is slowing that cat down. Okay, so the acceleration is going to be less than the acceleration of gravity because it's slowing the cat down.